In 2017, a group of students hauled a box to Arizona to run experiments in the state's arid climate. In the large transparent box sat a nondescript device. After one night, water droplets appeared in the box. Eventually, one of the students drank the collected water right on the spot. The experiment later confirmed the harvested water was the cleanest in the world. The mysterious object in the box was what is called a metal organic framework, which can harvest water from very dry air without any energy input. This is due to a historic invention called reticular chemistry. Its creator came from a water-scarce desert. This young boy, beaming with joy, is Omar Yaghi. Yaghi's parents are from Palestine, but were forced to leave their homeland and move to Amman, the capital of Jordan, where he was born. He and his 8 siblings lived in one room with their parents. Life was very tough.
We grew up in a home that had no amenities, no running water, no electricity, no plumbing. Okay, and in fact, we lived in one room. Half of the room was occupied by cows, and the other half is where we dwelled. We slept, we ate.
When Yaghi was a child, he was tasked with collecting water whenever he could. Water was only available once every 2 weeks, within a 4 to 5 hour window. So Yaghi had to collect and store as much water as possible in that short time.
You store as much water as you can within that 4 hours, and that's the water that you would use for those 2 weeks. If you ran out of water, you had to find a different source of water. So I grew up really appreciating the stress caused by water, and I lived it. And it affects all aspects of life. I mean, it affects which plants to put in your garden, how many cows can you have, and all these things are absolutely important consideration when you live in a water-stressed region.
The young Yaghi was very introverted. He would quietly observe the people and things around him.
Think that I spent almost my entire childhood watching things happening, watching my brothers playing, watching rather than participating. So I was more or less a passive child, but I was blessed by the fact that I liked to read, I liked to write, I liked academic things. And I would always wonder what things are made of. And this was basically my a lot of my time as a child.
Yaghi's love of learning is quite obvious in his only childhood photo.
You see that I'm holding a book. I would not even separate from my book to take a photo. I had it with me because I realized this is the most important thing that I would do.
For Yaghi, his escape from harsh reality was school. At the age of 10, he went to the library, opened the usually locked door, and stepped inside.
Went in, and I opened a random book, and in this book I saw molecular drawings. I didn't know they were molecular drawings. I just thought, wow, these things they look very captivating, and was very, very interesting. I kept this event secret actually from everybody because I thought I discovered something very, very interesting, and I didn't know how to describe it.
It was later that Yaghi began to understand that molecular structures and chemistry are the basic elements of everything around us. This made him even more curious. At age 15, Yaghi's father wanted him to study in the United States. He didn't want to go, but his father was insistent. He had no choice but to get a visa and board a plane to the US alone. With his brother's help, he enrolled in a local community college in New York. There, Yaghi was able to take some freshman-level college courses like English, chemistry, and calculus. Yaghi excelled and was able to skip from high school to community college.
calculus plus an English class, and I did very well. I did very well. At the end of the semester, I went to that same person. I said, you said that if I do well, I will be matriculated student. And I was, and I thought, oh my God, I'm in college.
During his studies in the US, Yaghi's interest in chemistry only grew stronger. He then decided to become a scientist. After his undergraduate studies, Yaghi continued to graduate school. There was a professor specializing in molecular research whom Yaghi sought guidance from. His first student project was a simple study of chemical reactions that ended up taking him a whole year. One day, the sample suddenly changed unexpectedly. The clear solvent had become murky and black. Yaghi was very disappointed. A classmate suggested discarding the sample, but he couldn't bring himself to get rid of it. Instead, he decided to use it for crystallization.
Well, the next day, sure enough, there were beautiful dark red crystals, sparkly. And I was thrilled. I knew that I've made something very special. And indeed, after we had analyzed those crystals, it took 6 months, but at the end of this journey, it was a very special compound. It was basically a compound that looked like a rice ball into which other small molecules could be trapped. And that was my first discovery.
It was then Yaghi began pondering a question. Could he go beyond the traditional method of mixing chemical components and heating them? His thinking was that this method left scientists unable to control the experimental process. Could a building block method be used to assemble molecules?
My desire was, could we build materials by a way like a Lego method, where molecules are building units, and then you program these building units to stitch together in certain ways to make new materials. So we wanted to really develop the logic of designing materials from molecular building blocks, because to me, that was more intellectually satisfying than mixing powders together and heating them up and letting thermodynamics take over and give you whatever was stable at that temperature. So we wanted to control those reactions, and that was really let's say, the desire or the intent at the very beginning.
During his time as a postdoc researcher, Yaghi began turning his idea into reality. It was then widely believed that building molecules wouldn't produce useful materials. The main obstacle was in crystallization, the most challenging part. Later, as an assistant professor at the University of Arizona, Yaghi was focused on tackling this challenge. Then, a Chinese student he had met in Nanjing contacted him, claiming he could do it better. Yaghi recruited him. Together, they overcame the difficulty in crystallization.
To make crystals is not easy, because the molecules need to get together in a very special way, meaning the molecules have to make an ordered, I liken it like going into a room full of kids and you ask the kids to make a circle. That doesn't happen spontaneously, okay? There's a lot of corrections that take place before those kids could form the circle. And that's exactly what happens with molecules. Molecules, they come together, and they may not come together at the correct orientation or the right orientation, so they have to break away and come back together again at the right geometry, orientation, spatial arrangement, so that they can make an ordered system, a system that is repeating throughout the crystal. That's not so easy to do, and we figured out the conditions, the chemical conditions, let's say the recipe, if you will, at which we can get molecules to do that.
However, crystals back then did not contain organic compounds. They were made entirely of inorganic compounds. Crystallizing them took 6 months, and then another 6 months were spent forming crystals suitable for structural analysis. Yaghi was very happy with the results.
But we were successful in that. We were very successful, and I thought, whoa, You know, as an assistant professor looking for tenure, I thought I was doing quite well.
Initially, Yaghi was trying to solve purely scientific issues, not practical problems. One day, a female student from China approached Yaghi, hoping to join his team. Other professors hadn't recruited her because her English wasn't good enough. Regardless, Yaghi accepted her. The student wanted to connect organic chemistry with metals. While Yaghi was very interested in creating new chemical materials, the many people who'd already tried to blend metals with organic ligands had always met with unstable results. So Yaghi was skeptical, but a year later, when he examined her research, he saw a groundbreaking discovery.
I realized that there's an opportunity there. And the opportunity was that instead of taking metals and linking them with neutral organic linkers, that's weak bond, we could link them with charged organic linkers to make strong bonds. And if we can succeed in crystallizing those, then we would have combined inorganic and organic building units to make what we now call metal organic frameworks, or MOFs. Well, that was the start, is that we were successful in crystallizing metal organics by stitching them with strong bonds, and that was really the start of the MOF field. So that was an important contribution back in '95, and the student that did it was this student that joined my group. Nobody wanted her because her English was not.
Then, in 1998, there was another significant advance. The question is, would these frameworks, after molecules had entered and been released from the pores, collapse or remain open? So Yaghi performed a crucial experiment. The results showed that substances entering and being released did not alter the structure. So even when nothing was inside, the framework stayed open. This proved that MOFs are dynamic structures, and that their porosity could be analyzed. In short, Yaghi had created a usable material. Then in 1999, the student from Nanjing took a crystallized sample from an experiment out of a chemical reactor and noticed it had lost its clarity. He thought his research results were now meaningless, but Yaghi found a way to resolve the issue.
And I said, no, you should not take it out of the reaction. You should characterize it while it is in the reaction mixture, and therefore it maintains its character. Well, it turns out that it is the most porous material that anyone has ever made. That was called MOF5.
This discovery established Yaghi as the father of reticular chemistry.
But I think in the case of reticular chemistry, Omar did the most important discoveries at the end. No, he just set up the basis of reticular chemistry. So yeah, I think he was for sure one of the pioneers in this field, without any doubt.
The most remarkable feature of MOFs is their high porosity that can trap other substances. A MOF about the size of 2 sugar cubes has a massive surface area.
I mean, you can really make materials now that you can absorb gases with a surface area. No, 1 gram of these materials will have the same surface area that a professional soccer field. No, so you can imagine how much molecules you can store inside these materials.
With Yaghi's growing reputation, he was made professor in chemistry at the University of Michigan and was later recruited by UCLA. By then, Yaghi had risen to prominence, but he sought greater academic achievements. So in 2012, he moved to the University of California, Berkeley. It was there that a student showed Yaghi some data that really surprised him. MOFs could absorb water even in low humidity environments.
But we discovered that not only does it take the water at low humidity, these MOFs, but also they release the water at 45 degrees Celsius, which is sort of a very high temperature in the desert. So I thought, well, you know what? That means that this moth, if I put it in the desert at night, it takes up water from air, and during the day, when it's in the daylight, it heats up. Now water can come off and I can condense water, I can make drinking water. So the fact that you can remove the water at reasonable ambient temperatures, like 45 degrees C, makes the material more energy efficient than any other material previously examined for this application.
To confirm the hypothesis, his students took moths to Arizona to run an experiment. They placed them in a large transparent box and opened the lid at night to let air flow in. Then, when day came, they closed it, letting the warmth of the sun heat it up. They later found water droplets forming inside the box. This experiment proved that moths really could harvest water, even in extremely low humidity climates. The students reported their findings, which left Yaghi astonished.
For me, it was powerful to see that you can make water in the desert with just the material, the moth, and the ambient sunlight. That meant that everyone in the world potentially can have their own device.
To further confirm their findings, Yaghi's students ran another experiment. This time, they went to California's Mojave Desert and used updated moths that put the air in full contact with the moths. They also attached solar panels to increase the temperature. This time, they harvested even more water. 1 kilogram of moths could capture 1 liter of water per day, demonstrating that moths not only absorbed water without energy input, but with energy input, they could harvest even more. This did much to bolster Yaghi's confidence in moths. All around the world, many regions still face water scarcity. If moths could be mass-produced at low cost, those regions lacking water or clean water sources could achieve water independence affordably and effectively.
We have a major chemical company that is scaling up these moths in multi-ton quantities already. Okay? And the parts that the device is made of are off the shelf. So your cost turns out to be just the cost of electricity. But if you don't want that cost, then you could use the independent device or the passive device that doesn't use electricity. So there are many, many options, and I have no doubt that many versions of this technology becomes available to everybody.
Since establishing the field of reticular chemistry, Yaghi had been exploring the possibility of capturing CO2 with moths. Experiments have demonstrated that moths, due to their high absorption capacity, can easily absorb CO2 from fuel gases. But to effectively combat global warming, it would be best to capture CO2 directly from the air. This, however, requires filtering out other gases, significantly raising the difficulty. A series of experiments showed that moths did not perform well in repeated use for that purpose. To address this issue, Yaghi developed covalent organic frameworks, COFs, which are porous crystalline structures made of light elements like hydrogen, carbon, and oxygen that can form strong covalent bonds.
And that's where we design materials, not just moths, but also another class of materials we call covalent organic frameworks that we invented in 2005. We can functionalize them in such a way and design their interiors so that they can seek out CO2 from air selectively and concentrate it in its pores. And that's why we moved to COFs. And COFs, unlike moths, their backbone is made from strong covalent bonds that are stable in acid, base, water, under a lot of corrosive conditions. And so we have recently invented a COF that works very well in terms of capturing CO2 from air.
All that remains is finding ways to mass produce it, and Yaghi doesn't think that is far off.
The devices are already built actually for CO2 capture. So we would then need to just scale up the material and make a form factor of it that is appropriate for the process. So I don't think it's we're not talking about years. We're talking about maximum of a year or so to show that these can work on a large scale.
The Yaghi Lab's fame attracts students from across the globe and resembles a mini United Nations. This student is operating instruments to test the performance of coughs. He places the coughs in a chemical test tube and inputs air from Berkeley, and then measures the concentration of CO2.
So for this experiment, we are showing that the material is capturing CO2 from Berkeley air. So we can see this is a measurement of background of Berkeley air, and the CO2 concentration is around 400 ppm. And as the cough material exposed to the air, the CO2 concentration dropped down to 0 until the CO2 finally breaks through the material. And this area indicates the CO2 captured by the cough.
The student adds that the trapped gases could also be used as a renewable energy source.
我们是在吸附过程中把这个有二氧化碳的空气通进 cough， 然后呢，出来的时候那个空气里面的二氧化碳就全部被 cough 材料吸掉了。然后在这个吸附饱和之后，我们会进行一个脱附的过程。具体呢，就是把这个 cough 材料加热，然后再抽真空，这时候所有的二氧化碳就会再出来。 然后我们就可以相当于把空气里面400 ppm 的二氧化碳浓缩到100%的二氧化碳，也就是纯的二氧化碳。那有了纯的二氧化碳之后，我们就可以做各种各样的，比如说催化把二氧化碳变成甲醇，或者是直接把二氧化碳打入地下，然后进行这个 fuel 相关的生产。
Some students are working on purification.
就是有机合成以后的那个产物，它是。 有可能有原料，还可能会有一些副产物，然后纯化的一个过程。
Each student can find an area of interest.
我现在主要是做一些帽服或者是靠服的合成，然后用它来做气体的吸附和分离。这个就代表每一个就代表它一个原子，然后这个是代表它一个键，化学键。
Some students are focused on researching the porosity of MOFs.
This will give us a lot of information. So it will give us about the surface area of how much surface area we have per gram of material.
For Ali, studying under Yaghi offers many benefits.
I think there are so many aspects that I learned from being in Professor Yaghi's lab. One of the first important things is from a scientific perspective to be really critical about what we do every day in terms of science, how we look at different results and how we analyze the different results or data that we obtain from experiments and being really critical about them, thinking deeply about the scientific reasons or mechanisms behind what we do in our experiments more than ever before.
Professor Yaghi's teaching style respects students' independence. He gives them room to explore freely.
I think overall Professor Yaghi is very encouraging us to explore anything that we want. He is always very supportive whatever we want to explore ourselves during the research. And he also, like, whenever we have any progresses, we can always report to him, and he will provide very valuable guidance to us.
Yeah, I would say Professor Yaghi gives us a lot of independence to do the research we are interested in, and as long as we focus on one thing, and he will also utilize his resources, like some very other famous professors from elsewhere, and he will introduce to us, and we can collaborate to make the project done.
Another unique aspect is that Yaghi treats his students as his peers. This aspect left a deep impression on this student from Taiwan.
一开始的第一句话就是跟我说，把他当做一个同事，不要把他当做一个教授、主管或者老板。所以我对他的印象就很好，因为觉得说可以跟他平等的交流啊。
Yaghi has his own reasoning for this.
And so the important part in a research environment is that the student and the professor are at the same level, and that the channels of criticism and asking questions are always open. that the student does not feel afraid to contradict the professor. And once that happens, magic comes about. You create magic because now you have two people poring over a problem who are not afraid to say, I don't know, who are not afraid to share their precious idea. Okay? And so this system of mentoring allows you and the student to be at the same level. And therefore, you can exchange ideas, you can be free to ask questions without hesitating because you think, I don't know enough about this or that.
This is actually one of the main reasons for Yaghi's success. Holding a model of MOF5, a treasured object, Yaghi says that it's not only the first crystal to break the long-time record for porosity, it also represents the dedication of a teacher and his students.
It highlighted the importance of the professor-student relationship, mentoring relationship, is that you need both for discovery. The student is there carrying out the experiment and making observations and making decisions on which observation to pursue and which observation not to pursue, right? Because you're targeting something. You can't pursue every single observation. So there's a decision making. And so if the professor is too far away and the student makes the wrong decision, then it goes undetected. So I think the collaboration between the professor and the student is so important in making the right decisions as to which observation to pursue. And in the same way, the student, not only are they doing the work in the laboratory, but they are asking questions that you may not have thought about as a professor. And so the mentor-student relationship, which is the basis of research in many countries, is a gift to us, is a gift to humanity. Because without it, you cannot make formidable discoveries. And it's the way science, we innovate in science, because we give our knowledge that we have accumulated over the years unconditionally to our students, knowing very well that one day they will go and they will be our competitors, but yet we still give them our know-how, we still give them our ideas, we still give them the support unconditionally. And I think that that's an important way of passing on creativity, innovation from one generation to the next.
Reflecting that he himself skipped high school for university, Yaghi sees the power of early education.
But I think that this ability for anyone to plug into the American higher education system is so powerful. It's so powerful because it provides opportunity for people to show that they can do the work. And if they can do the work, then they go to the next level and the next level. And that's really the story of my life.
And that is why Yaghi established the Berkeley Global Science Institute, hoping that young people could gain early access to the most advanced scientific knowledge. His idea was for an organization that allowed young people still in their own countries to connect and explore chemistry. How wonderful that would be, because professional labs are expensive and not every country can afford them. So Yaghi wanted to have an organization where young people could access the most advanced knowledge from their own countries. He set up research centers in Vietnam, Malaysia, Saudi Arabia, Argentina, and Jordan, among other places, enabling scholars embarking on their careers to participate in research through mentorship programs. So far, hundreds have benefited. Yaghi's open-minded approach has helped even well-established chemists also visit. Professor Maspach, a renowned scientist in Spain, recalls that when he first spoke with Yaghi, he was impressed by Yaghi's willingness to share.
I mean, impression was, I mean, you can just be amazed of, when you talk to him, I mean, you see how he sees the chemistry, his passion for the chemistry, and that he's very open to everybody. No, this is, I mean, my impression was, I mean, more than positive at that moment. No? And he's another nice thing, and this is my opinion, is that he's always trying to help, especially young scientists as me, and I know as others. So this is very good, especially coming from one of the founders of this field.
The principles of reticular chemistry are not patented. Anyone interested can use them. For the field of chemistry, Yaghi's standout contribution is that he distinguished himself in two fields.
To the chemistry and material science fields, no, and communities, is a whole new way of thinking how you can make materials, not porous materials, and this is very important. Not only metal organic, but also purely organic, no? Which is, I think it's amazing.
Now, numerous institutions and academic communities are researching reticular chemistry all around the world.
And many spin-offs and startups are working on this. I mean, both in Europe, Asia, United States. I mean, there are many companies that are starting to work, not together, but trying to solve all these problems for these many different applications.
Yaghi's contributions have earned widespread recognition, as well as many accolades and awards, like the Albert Einstein World Award of Science, the Wolf Prize in Chemistry, and the Vin Future Prize. He was also granted Saudi Arabian citizenship. His inventions have led to dozens of startups worldwide. Over 100,000 materials are estimated to have resulted from reticular chemistry research. According to Dow Jones Market Watch, the MOFs market was valued at $270 million in 2021 and shot up to $350 million in 2022. It is estimated to go even higher, to $685 million by 2034. Yaghi, known for his zeal for research and teaching, also stands out for his eagerness to try new things. So he became fast friends with Jennifer Chase, Dean of UC Berkeley's new College of Computing, Data Science, and Society.
So Omar had never done any work in computing or data science or AI, but the two of us met each other, and he told me about MOFs and reticular materials in general, which are incredibly cool. And he said, but we're still using 19th century methods for creating these. He conceives of them. I've never seen anyone embrace new ways of doing things as fast as Omar. I mean, Omar was basically saying, let's leave behind everything I've learned in my career and create a new way of making MOFs, metal organic frameworks. Omar is just, he was the first scientist I met, experimental scientist, who said, let us rush forward and do this.
Together, they founded a research group to apply the latest technology to all aspects of reticular chemistry.
We have LLMs, these large language models like ChatGPT, running all different aspects of the lab. They run the literature search, they run the optimization, they run the robots, they run the 3D printing. They are the project managers. So we have separate LLMs. We have 7 of them doing these things. And we're also now using foundational Gen AI to accelerate the way in which you do chemistry calculations, which has been very expensive computationally. So, you know, in doing this, Omar is demonstrating the future of chemistry. And I think also the future of experimental science in general.
Students in Yaghi's lab are using technology to accelerate MOF building, for instance, using AI to identify optimal crystals.
And then save all the images to this local computer so that later on we can analyze all the data, feed them into any artificial intelligence model, to further guide us how to find the next better experimental conditions to try to synthesize these compounds.
Yaghi is very open to using the newest tech, which has helped prove that AI can accelerate MOF building.
Instead of a student taking 2 years to crystallize their MOF or COF, now we can do it in 2 weeks. We have demonstrated that.
And this is actually one of the reasons some students seek to study under Yaghi.
想说透过 AI 能够加速研发的过程，那如果我们能够更快的找到更好的材料，那这样子就可以把网格化学的应用性弄得更广泛。然后也有可能另一部分 AI 的话 ，AI 可能可以让它变得比较普及化，就是说可能每个人都有机会用 AI 作为一个辅助的工具。你不用真的完全了解，花很多时间了解网格化学，但你可以透过 AI 来让你从网格化学的原理上做出你想要的材料。
The reticular chemistry pioneered by Professor Yaghi realized the concept of air economy. His inventions can transform air, which costs nothing, into valuable substances.
Taking components of air and using them to address a societal problem. Water is in the air, take water out of the air, make it drinking water. We're not destroying water, it just comes back up, okay? So it's a cyclable resource. CO2, in the fullness of time, not just capturing CO2 from air, but converting it into a renewable fuel, again, builds economies around that aspect. So already you have clean air and clean energy and clean water.
It was for this reason his science is a sustainable science, capable of addressing the toughest of humanity's challenges.
He moves chemistry, climate, and sustainability and the world forward with his science.
His winning the Tang Prize filled Yaghi with joy, and he spoke with heartfelt emotion during his acceptance speech.
As I reflect on my journey, I am reminded that life seldom offers perfect conditions. We often find ourselves waiting for the right moment, the right resources, or the right circumstances to begin pursuing our dreams. But if there is one thing my life has taught me, it's that waiting for the ideal conditions can often mean waiting forever. The key is to start wherever you are, with whatever you have, and to trust that with sound thinking, the journey will shape itself as you move forward.
During a sit-down meeting with high school students, Yaghi especially shared with them the route he had to take every day as a child.
This stop at my father's shop was absolutely essential in making me appreciate the quality and hard work. I was taught I would help my father with the chores in the shop, cleaning the tables, cleaning the windows, making sure the shop looks very shiny, very appealing to the customer. So he taught me that if you want to do a job, you have to do it well. Otherwise, don't do it at all. That's what I was taught day after day after day. You have to do the job well and you have to do it completely. Otherwise, don't do it. So I learned the work ethic.
Yaghi also advised the young audience to start with whatever catches their interest.
You may be interested in a lot of different things, okay? My advice is that to just pick something. Just look at all these things that you like and pick the one that is drawing itself to you the most, okay? Just pick something, anything, for God's sake, anything. And once you do that, and you start digging deeper and deeper and deeper into that object, you will become interested in that topic. Now, don't worry about the other topics you're interested in, because once you're proficient in one, you become intelligent enough to be proficient in others.
Yaghi traces this wonder to the very beginning of his story. That day he saw a molecular structure. Even now, he still can't explain it.
It didn't come from deep thinking about their potential, the possibilities. As a child, I think I just discovered it and I was attracted to it. And I think we need to be open to that. Not everything in life has to be explained on the minute level, especially at that stage of one's life, is that we are sometimes attracted to things and we have to accept them. I felt like I am being drawn by those molecules, right? It's almost as if I met another person and I fell in love. I was drawn by them. And they entered my heart, you see? And I think that then in the future, that interest, that passion is strengthened by knowing more about what they are, what they do.
Looking back over his life, Yaghi has no doubt that his parents' love and guidance were the decisive factors in his success.
In many ways, I lived in an environment that was really very supportive in terms of the love that our parents gave us, the care that they have given to our education, the care that they've given to our well-being.
He also had the courage to walk his own path, choosing not to follow his parents' wish for him to become a doctor.
That there are stages in our life where we sometimes have to say, you know what, this is what I'm interested in, and I know I love my parents. They spent their whole life and savings to get me to this stage. But at some point you have to say, you know what, that's it. I'm going to be independent and this is what I love. And that's something that I did at a young age. I decided that I will do whatever I like as long as I'm performing well. Then everything will be all right.
On the future of reticular chemistry, Yaghi says he aims to help countries address uneven resource distribution.
Almost 90% of people of 30 years old or less live in the developing world. There is no peace on this planet. There's no well-being of this planet if we cannot bring these people along, okay? And I see AI, and in a small way, reticular chemistry, as a way, if we build these platforms that I'm envisioning, where anybody can plug in and learn how to do research using those LLMs that I have discussed, then perhaps we can provide opportunity for people everywhere, whether it's in research-strong countries or in developing countries or poor countries. We give them opportunity to learn and plug into research and start improving themselves, their mind. And in so doing, you are improving the quality of their life. They're improving their quality of their life. You're allowing them to have tools to do that. So I see this as really my next frontier, the next challenge.
Beyond numerous hours in the lab, Yaghi enjoys gardening. His home sits on a small hill with a large garden in the back. He's planted many plants, and he knows each one like the back of his hand. He even has some fruit trees. He finds joy in nurturing them. One flower in particular, a hybrid he created, has multiple colors. He named it after his mother. It shows he is still close to his roots. Though he grew up in the desert, he now flourishes in a world of vibrant green. His passion for science and dedication to nurturing knowledge mirror his life. A sturdy plant, once rooted in the desert, now blossoming in full glory, offering a beacon of hope for a sustainable future for all humanity.